So earlier in the year when we first talked about energy, we focused on thermal and phase energy. So we focused on the energy associated with how fast our particles are moving, and we looked at the energy associated with what state of matter our particles were in. And we said those two things were pretty closely related. So now that we've started talking about the connections between particles, these actual chemical bonds, we can talk about something called chemical energy. When we talk about chemical energy, we're focusing on a word called enthalpy. And enthalpy is the sum of the internal energy of a system. So we're looking at the energy inside the bonds, the energy that's used or released forming and breaking bonds. That's what we're focusing on here. The symbol for this energy is a capital H. So capital H is related to enthalpy. We're going to most often use something called delta H, which is a change in enthalpy. So we're looking at that change in the internal energy of the system. So we're looking to see if we need more energy, if energy is going up, or if energy is being released from our system. So if we have a positive delta H, that means that our process is endothermic. That means we need an increase in internal energy. And this is usually seen when we're breaking chemical bonds. So you have to supply energy to be able to break bonds apart. If you think about if you are trying to physically break something, you have to use energy to break that thing, whatever it is that you're breaking. If we have a negative delta H, that's an exothermic process. And we usually see exothermic processes when we are forming new chemical bonds. So when we're looking at a reaction, we're looking at this balance between how much energy is needed to break the existing bonds and then how much energy is released when we form the bonds. That determines whether something is overall positively, has positive delta H, so it's endothermic, or if it overall has a negative delta H, which would make it exothermic. So let's look at two examples of some reactions. So our first example is sodium bicarbonate decomposing into sodium carbonate, water, and carbon dioxide. We did this in our types of chemical reactions lab. We looked at this decomposition. Now, this reaction has a positive delta H of 129 kilojoules. This means that for each mole of sodium, or for each 2 moles of sodium bicarbonate that we decompose, we're going to need 129 kilojoules of energy. Since this is a positive delta H, we know that this reaction is endothermic. And we know that from looking at this delta H value. We can't decide that simply by looking at the reaction. The reaction itself doesn't tell us that. It's this delta H value that tells us whether or not it's endothermic. So what this means is we are breaking bonds here with our sodium bicarbonate. We're forming new bonds to form the sodium carbonate, the water, and the carbon dioxide. Since it's endothermic, it's going to take more energy to break those existing bonds than we'll get back out when we form the new bonds. So it's this side that's going to win. It's going to take more energy to break those bonds. Let's look at our second example. Our second example is calcium oxide reacting with water to form calcium hydroxide. And from this, we can see that our delta H is negative 65.2 kilojoules. This negative right here tells us that this is an exothermic process, which means we get more energy out when we form these new bonds than it takes to break these existing bonds. In this case, it's the product side that is going to release more energy than the reactant side is going to take. So that excess energy is going to come out of the reaction, and this would feel hot. If we were to do this in a test tube and we felt this, this would feel hot to us because the energy is leaving the system and coming out. So that's an example of an exothermic reaction. Again, we can't see it just by looking at the balanced chemical reaction. We see it from this delta H value. Since it's negative, we know that it's exothermic. Okay, so at this point, I want to ask the question, does the amount of energy needed or released, so this number right here, depend on the amount of material present? If you have more stuff, do you get more energy? If you have more stuff, do you need more energy? Well, yeah. Think about a fire. If you have more fuel to burn, your fire is going to be bigger, you're going to get more heat out of it, you're going to get more energy. If you have more stuff that you have to burn, it's going, or not to burn, that's not a good example. If you have more stuff that you need to go through a chemical reaction, if we use our sodium bicarbonate, if we have a little bit of sodium bicarbonate versus a lot of sodium bicarbonate, it's going to take a lot more energy as we increase the amount of sodium bicarbonate that we have. So the amount of material present is definitely related to how much energy we're going to get out, and that's what we're going to look at next. So in our first example, we're going to stick with our sodium bicarbonate decomposition reaction. So 2 moles of sodium bicarbonate decomposes into 1 mole of sodium carbonate, 1 mole of water, and 1 mole of carbon dioxide. And we already know that it takes 129 kilojoules of energy to do this. So here's the question. How much energy is needed to decompose 3.5 moles of sodium bicarbonate? So here's how we're going to set this up. So we have 3.5 moles of NaOH to start with, or sorry, not NaOH, NaHCO3, our sodium bicarbonate. Now looking up here, so now we're going to look at a combination between our coefficients and our delta H. And this tells us, since we have a coefficient of 2 in front of our sodium bicarbonate, for every 2 moles of sodium bicarbonate, we're going to get, or we need 129 kilojoules of energy. So since I need to get rid of my moles unit and I want to end with energy, I want to end with kilojoules because my question asks how much energy is needed. I'm going to put moles on the bottom to make those units cancel, and I'm going to put kilojoules on top. So my moles will cancel. Now the question is, what numbers do I put in? Well, this information up here says that for every 2 moles, we need 129 kilojoules of energy. So for every 2 moles, we need 129 kilojoules of energy. And we can use this ratio to figure out how much energy we're going to get from 3.5 moles. So I'm going to do 3.5 times 129 divided by 2, and I get a total of 225.8 kilojoules of energy. Notice in my problem I have more than 2 moles. I have 3.5 moles. So I know I'm going to get more than 129 kilojoules of energy. Well, is 225.8 more than 129? Yeah. And it's a little bit more because we have a little bit more stuff. We started with 2 because 2 is our number from our balanced chemical reaction. 3.5 is a little bit more than 2. So 225.8 is a little bit more than 129. So that makes sense. So if we have more stuff that we need to decompose, we need more energy to make that happen. Let's look at one more example. So in example 2, we're looking at iron 3 oxide reacting with carbon monoxide to produce iron and carbon dioxide. And so this is a balanced chemical reaction that's already given in the problem. Our delta H for this question is negative 26.3 kilojoules. So this is an exothermic reaction. When this happens, we're going to get energy out. So our question asks how much energy is released when 60 grams of iron 3 oxide reacts with carbon monoxide. Now, a couple of things I want to point out. So we're looking for energy, so we know our answer needs to be in kilojoules. So it needs to equal something in kilojoules. Our starting information, though, is given in grams. So we need to convert from grams to moles and then into kilojoules, because this tells us for kilojoules. Kilojoules per mole is what this is looking at. This is all in moles. So we're going to do our grams to mole conversion first. So if I have 60 grams of iron 3 oxide, now remember, to do this conversion, I need the molar mass. So I'm going to put the molar mass on the bottom and 1 mole on the top. And so if I find my molar mass of iron 3 oxide, I need my periodic table. So I have 2 irons, each with a mass of 55.845. I have 3 oxygens, each with a mass of 15.999. I get a molar mass on my calculator of 159.7. So if I do 60 times 1 divided by 159.7, oops, I get 0.376 moles. And now I can finish up this question just the way that I did in the previous one. I'm going to go ahead and erase this so I have a little bit more space. So if I have 0.376 moles of iron 3 oxide, and this tells me that I get 26.3 kilojoules out My coefficient in front of here is just a 1, so for every 1 mole of iron 3 oxide, I get 26.3 kilojoules. My moles will cancel, which is good because I wanted my answer in kilojoules. And now I'm going to do 0.376 times 26.3, and I get 9.9 kilojoules of energy. So if I had 60 grams of this iron 3 oxide, that's the same thing as 0.376 moles. And since I get 26.3 kilojoules of energy out for every mole, I get 9.9 kilojoules of energy total. Because I have less than a mole, so I should have less than 26.3 kilojoules of energy out. And so that's how we can use these delta H values to figure out how much energy we're going to need or get from a certain chemical reaction based on how much of the reactants we have.